Let's do the different scenario, and I will write the equation. So, for example, the easiest one that you might have is a constant volume or batch reactor. Constant volume. So this is the liquid phase or the gas phase when you don't have the change of the moles. So basically you are dealing with the constant volume. If reaction occurs in liquid phase, or gas phase reaction, or gas phase reaction in a rigid batch reactor, in a rigid batch reactor, your V is going to be equal to V naught. So basically you don't have any changes. So in terms of the concentration, so whenever you are dealing with the constant volume, your best bet is Ca. So would be Na over V, or would be Na0 times minus X over V0. And in other words, Ca always is Ca naught 1 minus X. So similarly for Cv, you will write Nv over V, and then that would be Na0 over V0. Theta B, the reason we bring up these theta things, I'm going to just mention in a moment. Let me just finish this expression. Ca naught theta B minus VAX. So you can write the conversion. I mean the theta. Let me just put the definition of theta on the board. So theta I, in general case, that can be A, can be B, can be C, can be D. So it's Ni0 over Na0 is the ratio of the moles, right? And if you want to write versus the concentration, would be Ca0 V0, which is volumetric flow rate, over Ca0 V0. And then if the V's are constant, so it's what would be Ca naught over Ca0. Or in other words, you can have yi0 over ya0. So the point of theta is that we want to write everything based on the limiting reactant. So if you didn't want to write the limiting reactant, Cb would have been like Cb0 times, if it's in the left-hand side, it would be 1 minus xb, not xa. But by convention, we agree that x would be conversion of the limiting reactant, right? So not to get confused. Otherwise, always say, oh, this is the conversion of the A, conversion of B. Any reactants can have a conversion, right? Conversion is change. But we focus on the conversion of limiting reactant. So the reason is that limiting reactant finishes faster. So therefore, whenever we say X, we mean X of A, the limiting reactant. So this theta is defined to relate everything to 1x, to xa. So we convert it depending on the ratio of the moles. Theta B would be a ratio of the mole of B to the A, and C would be C to the A. Basically, we convert that fraction of the B, C, D conversion of that one to the X, which is conversion of X, conversion of A. So similarly, for this one, we can write it down the same formula for the product, which is Cc is Ca naught theta C, okay, theta C plus Cax. Again, X is the conversion of A. And CD is CA0 theta D plus DAX. Okay, so this is what we do with the over and over, not only in this chapter, but in the future chapters. This stoichiometry is going to hang on with you for the rest of this semester or thing. So it's going to be always with you. Questions? Oh, okay, so we just did. Anyway, let's do, for example, the constant volume, the same reaction. If we have, let's assume we have A plus B gives C plus D, okay, and we are dealing with a constant volume, okay, and let's assume that our rate of reaction or kinetics is Ka Ca Cb, which is elementary type reactions. Okay, so elementary is when the order follows the stoichiometry. So Ca, again, based on what we said, your Ca, concentration of A, very easy, that would be Ca naught 1 minus x, and your Cb would be Ca0 theta B minus Bax. Okay, I'm going to just flip the page, just write down these two equations. Just, we haven't started the gas reaction, so you will see that when we are going to the gas phase reactions, these equations, the numerator remains the same. In the denominator, you will get the change of the volume, right? So that's the only difference, and it's a big difference. So you will define a parameter called epsilon, and then you have to calculate epsilon and put it here. So that's for the gas phase when it changes. So basically, a stoichiometry will change. The type of the stoichiometry changes. Otherwise, the other, again, the same regulation holds through, right? Starting with the design equation, and then kinetics, and then stoichiometry. Okay, so the RA, the reaction, minus RA would be KCACB, and that would be K Ca naught squared 1 minus x times theta B minus Bax. For obviously that's very obvious. For equimolar means the same molar feet for A and B. So theta B would be 1, correct? If they are equimolar, A and B, theta B would be 1. For a stoichiometric feet, for stoichiometric feet, if the feet follows the stoichiometry, obviously theta B would be B over A. But this is the information that you need to be provided when you are dealing with the equations. Okay, so just another example. You see, just the form of the. I will change the form of the kinetics. Like if the kinetics, kinetics or rate law is minus RA K Ca squared Cb. Okay, again, this is going to be the equation like a 2A plus B gives us C plus D. And again, we are dealing with the constant volume for now. Constant volume. So your minus RA is K CA naught cubed 1 minus X squared theta B minus BA X. If you're going to just plot this one's 1 minus RA or FA naught minus RA for the flow reactors, you're going to get something like this. I'm going to set a workshop on the polymath very soon. I mean, gives you at least one single sessions. If you want, you can do it more. Just to show how this one works. It's very user-friendly software. And as you might see as you go further, most of the time you won't be able to hand calculate the equations. There are non-linearity there. There are more equations involved. So you need to do something. So that polymath is very cheap software, although you have it free for this course in room 201B, computer room. All computers have this one. So just go and play with it. So it's very handy. It's not only is good for this course, but you can use it for solving ODEs, which you need it for any other courses, or PDEs. It's very easy to have. So just you write it down. Basically, you're typing with the equations. That's all. There's no programming involved at all. So it's an interface. You have to get familiar with basically with the interface and just type it in. And then computer does the work for you. Okay? And it's cheap. You can even download it in your laptop for like a short period of time. Okie doke. So I'm going to do another example. Okay? So I do so many examples as much as I can in the class. So because I believe the course can be understood through the examples, right? I can finish practically the book within 3-4 lectures, the whole book. And that's what I did for the graduate course. I have a graduate course now with the same topics. I mean, the title is Advanced Reactor Design. So what I did, because we get sometimes international students with different background, so I covered the whole book in 4 lectures. It was like kind of sweep through this. And then we get to the more advanced material that we don't get it in your course. I mean, I wish chemical engineering program in our school had 2 courses. There are lots of programs in board that they have 2 chemical engineering, 2 reaction courses, but we do have 1. And I guess one reason is that we have like the whole program is oil and gas and chemical, and I guess for oil and gas, the students are not mandatory to get the reaction, right? Therefore, so they try to distribute the resources equally between the two programs. Otherwise, it's a very it's a fundamental course, as I mentioned in the first lecture. So this is what all chemical engineering related people should know. It doesn't matter, is it food engineering, is bio, is oil and gas, is whatever. So you're going to have reactor in your system, no matter what. Even reactors in your body, you know, your stomach is kind of a reactor, like it applies enzyme. An enzyme, when you apply enzyme, is a reaction happening in your stomach, right? But this is a biochemical reaction. So everywhere you can see that can be as small as a few micron. The reactors can be as small as a few micron. It can be as big as like this room. So it's a very expensive topic, and it's kind of complicated. But when you know the fundamentals, you can apply it. This is a side story. Anyway, the example wants you to calculate the equilibrium conversion for gas phase reaction. For a gas phase reaction, meaning XE. We want to calculate XE. So data, consider the following elementary reaction with Kc equal to 20 d-meter cube over mole, and Ca naught is 0.2 mole per d-meter cube. And let's assume that our reaction is 2A gives B. And obviously we want to calculate given all this information, calculate XE for a batch reactor. So whenever we are talking about the equilibrium, so we are talking about the reversible reaction, right? Because A gives B, B gives A, or A2A gives B, B gives 2A, correct? So we want to know what would be the equilibrium value. So the maximum conversion always is the equilibrium. So sometimes you might change the question and say, what's the maximum conversion? So it means that you allow enough time just the reaction goes to completion in equilibrium stage. Also, some reactions never get to the equilibrium. There are reactions that they are not thermodynamically stable reactions, so they go to some extent and then they stop at that. And you have to change the condition if you want to push them forward. Or use the Le Chatelier's law. Remember from physics what it does. So you make a change in the system. Specifically speaking about the reactions, you just remove one of the products out of the system, and then basically based on the Le Chatelier, you are pushing the reaction forward from left to right. That's what we use for CO2 capture, which is one of my area of research. So we try to capture CO2, to remove the CO2 from the system, and then push the reactions forward. And we get double benefits if the hydrogen is produced with that reaction. So we get more hydrogen, and obviously more CO2 is captured. But if no changes has been made, basically you consider equilibrium stages. Okay. So this is a very routine problem. You might take questions in the midterm in this fashion. So that would be first we start with the reactions, the kinetics or rate law. Minus RA is KA CA squared minus KB CB, and then you factor the KA, would be KA CA squared minus CB KA over KB, and that would be KA CA squared minus CB over KC. Where KC is KA over KB. So at equilibrium, what happens at equilibrium? What is the condition of equilibrium? The overall rate would be 0. So basically your RA would be 0, right? So if his RA is 0, so you just equalize this equation to 0, and then find CA from there. So it would be 0 is equal to KA CAE squared minus CBE over KC, and then from here you can calculate KE. Sorry, this should be KE. Okay, KC. Yeah, KC or K equilibrium. So you can calculate the K equilibrium from here. You can calculate the K equilibrium from here, which would be at equilibrium, because this becomes equilibrium. If your rate becomes 0, this K would be equilibrium. So KE becomes CBE over CA squared. Okay, so what should I do in order to calculate the equilibrium conversion now? What would be the next step? The next step would be to form the stoichiometric table. And it's a batch reactor. We know the reactions. We write down the stoichiometries, and then we use these equations. How much would be the B at equilibrium at the final? How much would be, because we don't have this value yet. And then when we get these values from the stoichiometric tables or stoichiometry, you just plug it in here and then you find X. I mean, when you get advanced, you can even do it in your mind, quick calculation. But I don't recommend it, because especially when you have few components in your system and you have inert system, there are always sources for error. So we're going to just do a very quick table there, make the table. So the symbol initial, that's exactly what I did the other day. So initial change, and then remaining. Okay, so we have A and B. We have initially NA not in your system. We have 0 of B. So how much changes we have, given the fact that our equation is 2A is B. So you are going to have minus NA0X. This is the definition of the conversion. And what is left would be NA0 times 1 minus X. And for the change, the production of B is 1/2 of NA0X. And then the remaining would be NA0, the production of B X2, X over 2. Just keep in mind, when you write the equations for the tables, for this table, always you look at the forward reactions, okay? So when you put it in the equations at the end, even if it is reversible reactions, the equations will take care of the reversibility of that one, okay? Don't get yourself confused of the reversible. So when you write this one, so write it down forward. Reactions, like what is the change, what is the remaining, what is the change, what is the remaining for all the components. And then if it's a reversible reaction, so when you are putting in the equations that we derived over there, so that will take care of the reverse reaction. Yes, please.
What's KB?
What?
KB, what's KB?
Where do I put the KB? Oh, okay. So that's Ka is the forward reaction. Kb is the backward reaction. So for the reversible type, so
when it relates to A.
No, it relates to the B. The reason is that you have two molecules of A. This forward reactions is based on the molecules of A. Then KB is a separate entity, so they are not related. So, but when you are going to the reversible reaction, then that equilibrium value, which we call it Kc, would be the ratio of these two. However, for the kinetics, because we are dealing with the reactants, we just focus on forward reactions. Yeah. Sure. Yeah, sure. The same questions? Yeah. That's another question. Okay, so what is this? Is Na0. So let me just here. So when you initially you have Na0, based on definition of the conversion, you have minus Na0x used in the system, and obviously the remaining would be Na0 1 minus x. So how much B is produced? The 2 moles of the A gives 1 mole of the B. So basically 1/2 of the Na0x, and this would be Na0. This is Na0 x2. Basically the same. Na0. What was wrong? Oh no, sorry, that's minus. So it's Na0. Is it good enough? Na0. You know, after when you get your confidence in whatever you do, so you lose like a little bit of the how do you write it down. So have you gone to the doctor's office there? You see how they write the prescription. That doesn't mean that they cannot write nicely, but the thing is that they have done it over and over for years. I mean, after a while, they just but anyways, I try not to. Na0. Yeah. Okay, so the total would be like Na0, Nt0. The initial would be Na0, and then the total remaining obviously would be Nt for the final would be Na0 minus Na0 times x2. So to avoid these things, I try always to speak out when I'm writing it down. So in case if you listen such cases, you might avoid this kind of confusion. At equilibrium, so we have minus Ra is equals 0, and then again, as I wrote already, so I wrote this one in the previous pages. Ke would be Cbe over Ca squared. I'm gonna just plug it inside. So it would be Kc would be Cbe over Cae squared, and that would be Ca naught Xe, Ca naught Xe over 2, that would be Ca naught 1 minus Xe squared. Okay. So keep in mind that this is a constant volume, correct? Therefore, if you divide these ones by the volume, doesn't matter the initial volume or the final volume, that gives you the concentration. Okay, the mole over the volume is the concentration. Okay, so therefore this is going to be Ca naught over x2, and then Ca naught times 1 minus x would be the final concentration. Because in this equation we are dealing with the concentration, correct? And the concentration is given as a data of the equation. So we have data. We have Ca naught to be 0.2 mole per liter, mole per millimeter cube, and Kc was 20 liter over mole. Okay. So now if you plug in these numbers to this equation, so your KE would be XE over 2 CA naught 1 minus XE squared, and then you can find from this equation XE if you plug all the numbers. So you can have XE to be XE, you will find it 0.703. This is the questions, if you want to do this in the final, will be similar fashion. So you have to know. I mean, if we do the flow system, which I'm going to do it next lectures. So I'm going to introduce it, and then I will make up the table next lectures. So the same criteria, and then we just replace the C with the F. So that will do the trick for you. Okay, so just if you, I'm going to flip the page. So write it down. Just as I mentioned, just for the sake of completeness, I'm going to just quickly put the same stoichiometric table for the flow system. So exactly the same. Nothing is going to change. You will see that one. We were dealing with the moles in the previous table. Now we are going to just replace the moles with the F, which is the flow rate of each component for the flow system. Okay, so the title would be flow system stoichiometric table. Stoichiometric table. Okay, so we have a reactor, any flow reactor that can be plug flow or CSTR. So we have inlet and we have outlet. So let's assume that we have our famous equation A plus BAD gives CAC plus BAD. Okay, A plus BAB plus gives CAC plus BAD, and we have the entering condition like FA naught, FB naught, FC naught, FD naught, and FI. For the sake of argument, we can always, just to make a little bit additional things in your questions, inert system. Like for example, you have nitrogen that goes from left to right. So what it does, it changes the total mole. So your mole fraction will change. Okay? And the outlet would be the same. FA, FD, FC, FD, and FI. So if you want to make the table, so we're going to have the species here. Then we're going to have reactor, feed, or entrance. So it would be like entrance. And then would be change. And then would be reactor effluent. Reactor. Okay, so we have species A. So FA naught is the entrance condition, and then how much is changed based on the conversion. Again, exactly the same value that we had in the previous table. So it's a fraction of if A is used, which we call it conversion, which would be FA naught times X. Okay, and what is produced is FA naught who is going out is FA naught 1 minus X. So for the B, then exactly the same. You have FB naught. So FB naught, you define it based on the FA naught. Again, this is the trick. So using the theta, you relate this FB naught to FA naught, right? So which would be BA times FA naught, correct? For theta B or theta B times FA naught. Okay, just to have everything based on the FA naught. And then that would be minus BA, again this theta is BA, FA0 times X, and then FB would be FA0 theta B, which is B over A minus B over A X. For the C, the same, but keep in mind that C is produced, so is theta C is FC naught, is theta C FA naught, and that would be CA plus CA. CA FA naught X, and that would be FA naught times theta C plus CA X. And for D would be theta D, FD0 is theta D, FA naught, DA FA0X, and that would be FA0 times theta D plus DAX. Okay, and then for inert, we have FI naught is FA0 theta I. How much is going to be changed for inert? Nothing. So then that for the final value also we have FA0 times theta I. So what would be the total? The total, if you add them together, you are going to have the initial total value with respect to the total moles, and the FT in your effluent would be FT naught plus delta FA0X. And from previous lectures, I guess we defined delta, did we? So delta is, what was delta? Remember? Delta was the change in the total moles of the system, basically would be total moles of the product minus total moles of the reactants divided by A. That was the definition of delta. Yes, please. Yes, yes, yeah. Basically, theta I means whatever is I, like CRNI over NA. What is? A. This is a limiting reactant. You're writing everything based on the limiting reactant. Like B over A, C over A, D over A, I over A. Sure. Okay, so let me just put this definition and then, so delta, do you remember what was the definition? No? So was D over A plus C over A minus B over A minus 1. The way that I just, so I myself will say D plus C minus B minus A over A. So that's the way that I do it. So basically the definition is a change in total number of moles, in total number of moles, okay, over mole of A, mole of A. And again, just to put for just these theta things seems a little bit awkward. So theta I is going to be Fi for over Fa0, or you can write it down based on the concentration Ci0 V0 over Ca0 V0, or if they are the constant volume, so it would be Ca0 over Ca0, and that would be Yi0 over the mole fraction over YO0, YA0. So that's the definition of theta I. So the same things for the batch system versus the reactor system. And also just the definition that the concentration is Fa over volumetric flow rate. If you are in the flow system, so the concentration is mole flow rate over the volumetric flow rate. We're going to do a couple of examples next lectures, so you will see that one, and also in the tutorial we do lots of these things. So the stoichiometry is a basic part of this course. So we try to understand it well, because the next step is the isothermal design, and always we are going to use this concept as part of the design criteria.